So for, I guess, historical information, I have no idea when store and forward was first created. I guess it's one of the first things anyone would think of. Cut through, there's, I think, a paper in the late 70s that probably was the first time that was talked about. Wormhole routing, I think, is mid-80s. And for reference, almost all of these networks on a chip use wormhole routing. And the big value is that I don't have to store a whole packet. I can have much smaller buffers, and the buffers are a significant amount of the cost of a router as far as space and power. I've seen some work that has talked about special designs of cut-through that reduce the buffering, but wormhole's pretty much standard. I designed one router that used cut-through, which is simple, and a little more complicated router that uses wormhole routing. I'm largely going to talk about the one that uses wormhole, sorry, not wormhole routing, wormhole flow control. The next topic is back pressure. So I said, you can send as long as there's space downstream. How do you know that there's space downstream, that the next router has space for a flit? So in this case, I'm talking about wormhole routing. So the way it works is the upstream router keeps track of how many slots exist downstream. So if I can send 4 downstream flits, then I'll know that that number is 4. And every time I send, I'll deduct from that number. And when it goes, so in this case, node 1 is communicating with node 2 and sending flits to it. Once node 2 sends a flit downstream, it's now got one more spot. And what it can do is send a credit upstream. Say, okay, I now have one more space. So upstream, you're notified that there's one more spot. So this way, every router keeps track of the space downstream. And I showed here, this is the round trip time of a credit. And the idea here is that, I said wormhole routing technically only requires one spot for a flit. But the problem is, as soon as this flit gets sent, I can't send out a flit immediately from node 1 until I get the credit back. So in practice, you use 3 flit buffers or something just to amortize the cost of the credit round trip time. Right, so in wormhole routing, you would do credits based on flits. With virtual cut-through, I don't need to, because I know as soon as I can send the head, I must be able to send the rest. So I would actually, and indeed I did this in the virtual cut-through router, a credit is only sent back when the head flit is sent downstream. And that way I know that as soon as I have a credit, I can send the rest of the packet through. And generally with a packet size, that's enough to eat the cost of this round trip time. If you don't have this, you get this sort of bubbling effect where your one spot in the router has to move all the way back downstream every time. All right. Wormhole routing, here's an example of what's called head-of-line blocking. So if I have a packet, this packet B comes from the top and goes out right, and at node 2 it gets blocked. One of the problems here is that because I'm blocked, I can't keep sending, and I only have space for, let's say, 1 flit. It blocked everything back, and I can no longer send A through. A also wants to go to node 2, and if I can't send to node 2 there, A gets blocked, even though, let's say, A needs to go to node 3. So you get head-of-line blocking here because B is in front of it. And so there's a technique that's called virtual channels. And the idea is that I have one physical channel here, but I'll multiplex it. I'll allow for 2 packets to be isolated. I have 2 separate buffers for the physical channel. And I'll send A here, but as soon as A gets blocked, I have another spot for B, so B can be routed down to node 2, and then, or sorry, I mixed this up. B here is blocked, but A can be routed to here and on to node 3 and step in front of node 2. The analogy I like is that this is like having a turning lane on a street. If my street is 1 lane wide and then right at the intersection I have a turning lane, I haven't increased the bandwidth of the actual street. It's not like more cars can go through, but anyone who needs to turn isn't blocking someone going straight. And that's the same effect you get here with virtual channels. That what I've done is I've increased my buffer space, but it allows me to jump in front of other flits that are blocked. Yeah.
Given that that's gone, it seems reasonable that what you want is a virtual channel per length so that for it's going to be a function of all the physical dimensionality. So I probably want a virtual channel for G3 potential outbound direction.
Yeah, so I mean, generally speaking, you talk about the virtual channels of this outbound port are exactly these virtual channels. That's because there's got to be a one-to-one mapping there. Typically, you have the same. So it's effectively the same if I just talk about the virtual channels at each input port. And the reason is that this is where I happen to be doing the buffering. Sure, if a packet comes from here, you're saying. Not necessarily. It's just dependent on, certainly it depends on your topology, but
that would be beyond that.
yeah, there's no use going beyond that, right, because you're blocked by, if you're going in the same direction, then it doesn't matter. So there's no use going beyond the amount that you have for your direction. So yeah, so in this case, if I have, assuming you can't loop back, you have 3 directions, there's no use having more than 3 virtual channels for the purpose of head-of-line blocking. My next slide will talk about other uses of virtual channels. And that's has to do with deadlocks. The definition of a deadlock, so a group of packets are unable to make progress because they wait on each other to release buffers. A more abstract way to look at it is that I have some resource dependence graph where my edges denote that I'm waiting for this resource to be released to acquire this resource. And if there's some sort of cycle in that dependency graph, then you can have a potential deadlock. And there are 2 causes of cycles. So one is, if due to my topology, routing, and flow control, the big 3 parameters of a network, I could just be routing packets in a way that causes a cycle that could potentially deadlock. And in particular, because I'm using a mesh and I'm using dimension-ordered routing, I don't have any potential deadlocks due to this. I only route along the X and then the Y, and there's no way to create a cycle that way. I'm not going to prove it, but it's pretty easy to convince yourself. The other aspect, which I think is pretty interesting, is that a high-level protocol, something using the network, could create a dependency here. So the example I give is a request-reply. Let's say I have, at one endpoint of my network, I have a client that is trying to send something out on the network, and it's blocking until there's space. Software blocking that until there's space, or even hardware, it doesn't matter. But it's blocking until there's space to send out on that network. And I'm sending a request to a server, also on an endpoint of the network, and that server is trying to send a reply packet to some request. I can be blocking trying to send the reply packet, and because I've now created dependency, right, to send my request, the server has to clear stuff out of the queues, and the server also is blocked trying to send a reply packet and has this problem that it's waiting for, they're both waiting for each other to release their resources, basically, and you get a deadlock because of a high-level protocol. So that's unrelated to the network. So typically what you'll do is that you'll do some sort of deadlock avoidance. So I'll talk about, again, the two causes to break cycles in the resource the two causes of the cycles in the resource dependency graph. Generally, what you want to do is you want to use these virtual channels to break cycles. And so if I have some topology, routing, or flow control that causes a cycle, I can use virtual channels to say, okay, at this point when you turn from the x dimension to the y dimension, go from virtual channel 0 to virtual channel 1, and never go back to virtual channel 0. This way I've created an ordering on the channels that will preserve this dependency. Because, again, the virtual channels are what define the resource. Every virtual channel is a buffer. But again, based on my construction, I don't have this problem, so I don't use virtual channels for that purpose. The other idea is that my high-level messages, I create separate message classes, and then each one gets its own virtual channel. So if I want to send a request packet and I want to send a reply packet, they're routed with different virtual channels so they can't ever block each other, right? Because their space is separate. And for reference, I think I've read cache coherency protocols are on the order of about 5 messages that you would see. And so generally you'd provide something like 5 different message classes. And note that this is separate from the use of virtual channels to prevent head-of-line blocking. Let's say I wanted to provide 2 virtual channels so that packets didn't block each other just for the purpose of performance. I would say, okay, I have 5 message classes, and I would have, for each message class, 2 virtual channels so that they didn't block each other. But each message class is unique. They don't ever work on the same virtual channel. Right. The interesting thing is that it's dependent on the semantics of the higher level protocol, right? If the higher level protocol has messages that don't create any dependency, or you do something like periodically you're just reading out of the FIFO, your software is in some way preventing any dependency there, then you don't need that aspect of virtual channels. But the other, yeah. That's true. Yeah, yeah, yeah. I think the interesting thing to point out there is it's completely dependent on what you're using the network for. So part of the way I've built this thing is that it's parameterized. You say I have this many message classes, I have this many ports, this is how wide my channel is, because those are all parameters you would want to set for your network, and you can't set them independently of whatever your usage is. All right, I'm switching gears a little bit here to talk about the microarchitecture of a router. So I talked about performance with respect to bandwidth and latency, and largely, there's routers and there's channels between the routers. And channels really come down to circuit design. But a lot of the performance, because you have short channels, a lot of the performance, the space, and power consumption comes because of the routers. And so how you specifically design a router becomes very important for all those different aspects of how you would measure a network. So just to give a sense of what I've drawn here, you have K input ports, and at each